And good morning again. Today we are going to go through chapter 8, nice and quickly. So chapter 8, we start with a ratio and proportion. A ratio, of course, is the comparison of two numbers, like a score in a water polo game or something like that. Where a proportion is the equality of two ratios. So 2/7 would be the same thing as 4/14 or something like that. A proportion requires there to be four numbers. It's tempting to say four different numbers, but they could all be the same. 1/1 equals 1/1. You could have different combinations of 1/2 equals 1/2, or 1/1 equals 2/2 of two different numbers. You could have three different numbers. I think we said 4/6 equals 6/9 as our class example. Um, and when you have three numbers, that one number which gets repeated twice is the geometric mean of the other two. It is halfway between the other two, not in terms of addition. It's not an arithmetic mean. It is a geometric mean. It is halfway through in terms of multiplying. Whatever I multiply 4 by to make it into 6, which is 1.5, I could divide 9 by and get 6. 9 divided by 3/2 divided by 1.5 is 6. Just like for a normal arithmetic mean, the arithmetic mean of 0 and 100 is 50, because if I add 50 to the bottom number or subtract 50 from the top number, I end up right there in the middle. Okay, we talked about proportions, proportional. In English, the word proportion frequently gets used when they don't really tell you specifically what the other ratio is. Like, oh, the number of lima beans that you eat in third grade is proportional to your IQ or something like that. They don't tell you what that proportion is, and obviously that doesn't sound like a true statement. We had one theorem here, one thing which we wrote in if-then form. It said, if a proportion exists, then we can cross multiply. Like over here, if I know that this is true, then I could say, oh, 2 times 14 must equal 7 times 4. 2 times 14, 28. 7 times 4, also 28. Of course, that's useful if they're not all four given numbers, if one of them is a variable. Okay, proportions come into play a lot in terms of similar figures. So a little bit of a roundabout approach in this chapter. We talk about what similar figures are. We're really going to give that definition, which is a theorem. Then we're going to go on to show how to prove that triangles are similar. And then we're going to loop back to using the fact that they are similar again to show other things. So if figures are similar, then they have two attributes, and those are these. If figures are similar, then their corresponding lengths are proportional. And I am very careful about saying the lengths instead of sides, because this can be any length. This could be perimeters. It could be semi-perimeters. Apophthegms, which we learn about a whole lot later, and my colleagues will tell me it's pronounced apothegm. Radius, a polygon has a radius. Side lengths, of course, are fine. Altitudes, medians, anything that corresponds and can be measured in length. The other theorem says if figures are similar, then their corresponding angles are congruent. Those are not in a proportion, unless you call that proportion 1-to-1. They are congruent. Okay. In Algebra 2, we will go on to look at similar figures in a different way and talk about them in terms of dilation. Sometimes they call them shrinks or compressions. There were a number of different ways of proving that triangles were similar. AAA works, but you would never use it because it is kind of redundant. What we learned in the previous chapter was that if two angles are congruent, two pairs of angles are congruent in two triangles, then the third pair is congruent. So there's no information that you would get from AA that you couldn't already know that you have AAA. I said that a little funky. There's no information if you had AAA that AA wouldn't tell you as well. AA, by the way, is the only one we would ever use in a proof. There are two others. There is SAS similarity, slightly different than normal SAS, which says if two sides of a triangle are proportional to the corresponding sides of a second triangle, and the included angle is congruent, then the triangles are similar. And the third one says that if all three sides of one triangle, this is the SSS one, are congruent to, or similar, of course, if three sides of a triangle are proportional to the corresponding sides of a second triangle, then the triangles are similar. Okay. There is no AAS like there is in proving triangles congruent, because if you already had AA, you would be there. So this section was all about proving triangles similar, and the next one was about taking it one step further. Once the triangles were similar, then saying that their corresponding lengths are proportional or sides are congruent. Sorry, we are back. So 8.3 was about proving triangles are similar. 8.4 was really about using that. So most of the steps in 8.4 involved something from 8.3. You would prove the two triangles similar. If it's in a proof, again, we're only using AA. And then you would go on to say that their sides are proportional, and conceivably even use that theorem from the first section, and then say if a proportion exists, then you may cross multiply. I recommend giving a look at something like that example 3 on page 346. I know that the resolution, I've been hearing reports that the resolution is not good enough for you to actually read it off here, but that's what it looks like, more or less. So they gave us that the triangles are similar. I would prefer an if and a then here. If triangles are similar, then their corresponding lengths are proportional. Thank you, Kat. And finally, instead of means extremes product theorem, which seems like an antiquated way of saying it, if a proportion exists, then you may cross multiply. I never particularly loved the sound of that because it's the only theorem we have which puts U into it. In section 8.5, let me get there. Section 8.5, we learned two other theorems involving proportions. There were 3 in the book. We only did 2 of them. One of them, the so-called side splitter one, says that if a line is parallel to a side of a triangle and intersects the other 2 sides, it splits those sides proportionally. So again, there it is, that length AB is to that length BC, as AE is to ED. And I like this one because AB is literally over BC, and in the proportion AB over BC. Notice I've got 2 parallel lines. Hey, 2 parallel lines make an equal sign. AE is literally over ED. This theorem works even if these don't come together to form a triangle. So if I were to continue to split this and cut off the top, truncate that triangle, I'd end up with a shape that looks like this. And as long as these lines are all parallel, these transversals are split proportionally. That really brings us to the end of chapter 8. Chapter 9's up next.